Right guys, today's session, capacitors in DC circuits. I'm going to start by just reviewing something that you probably will have already done if you've done something like BTEC, i.e. what is a capacitor. I'm not going to go too deeply into any kind of different constructions of capacitors. We're more interested in what they do in circuits. Okay, but first of all, a capacitor would consist of, we need some connector leads, two metal plates and some connections to connect into a circuit, and in between those two metal plates there's a layer of insulating material. That could be a range of different materials, from air, i.e. an air gap, all the way to things like ceramics and electrolytic materials, kind of like similar to what you would have in a battery. But it's a dielectric that is insulating. So the two blue bits are conducting plates, and the green bit is insulating dielectric. Okay? So the idea, what capacitors can do is, well, they have a level of capacitance. So we've got capacitance C, that's the circuit symbol for it, and then measured in farads. F, however, more typically microfarads, nanofarads, picofarads, because the farad is a very big unit, and so we're more likely to be talking in times 10 to the minus 6, times 10 to the minus 9, times 10 to the minus 12 farads. Yeah? So because the actual farad is really big, we're usually talking in those sub-multiples of farads. The amount of capacitance, so size of capacitance depends on 1, the area of the plates, we add to that more area equals more C, more capacitance. Yeah. Second thing, distance between the plates, closer equals more C. And 3, dielectric material. The difference that makes is a little bit more difficult to define. The dielectric material is more about the quality of how likely the capacitor is to keep its charge stored on it under certain conditions. And it's not so easy to say what the difference is between, let's say, a polyester capacitor and a ceramic one. It's more about the types of circuits and applications they're suitable for than it is about how much charge they store, although it will make a difference. But it's not like the plates thing. We know if we make the area bigger, we're going to up the amount of capacitance we got, and we know if we can squeeze the plates closer together, have a thinner dielectric, we're going to be able to store more charge. Okay, so that's the basics of what a capacitor is and how it's the kind of general construction. To get the area bigger, I tend to make the plates out of tin foil and roll them up and put in a can with paper or the dielectric in between them, and so on. The smaller values, the little ceramic ones, they're often quite tiny values anyway. Right, and where air is used as a dielectric will be in something like a variable capacitor. You have plates that move, so you're changing the area as the plates move. But you have a set of fixed plates, a set of moving plates going between them, so you can vary capacitance. Everybody okay with that so far? Yeah? Okay. Moving on then. So what happens when we need to consider what happens when the capacitor is connected. So there's our symbol for a capacitor, and if we throw a switch, connect that to some kind of source of voltage, like so. What happens when we consider what happens when we close that switch? So if we close that switch now, remember that the material in here is an insulating material. So in theory, absolutely no current can flow through that capacitor. If that was a perfect insulator, we can't get any current go from there through that insulation and into this part of the circuit. Okay, but if this is 10 volts, when we switch it on, a current will flow such that we start to put positive charges on this plate. We're going to look at that time it takes to do that in a bit more detail next week. Okay, but for now, eventually we get to a state where for every positive charge on this plate, there's a negative charge on that plate. I don't talk about it too often, but current flow is actually, we always say current flows in this circuit in that direction. Yeah, from positive to negative. In actual fact, current flow is a flow of electrons in the opposite direction. But I don't talk about that a lot because by convention we work with current flowing from positive to negative. Okay, so we'll think of it in terms of positive charges flow to here, leaving negative charges on the plate, because that's a process. Electrons flow from that plate all the way around the circuit and end up on there. We end up with a charge, and we end up eventually, in theory, with 10 volts across that capacitor after a small amount of time. And again, next week we'll talk about how long that time is and what affects that time. Okay, but for now, you can consider that a small instance after you connect that battery source to that capacitor, you would charge that capacitor up, so you got 10 volts across it. Okay, and then if we then do that, disconnect the source, we've still got 10 volts across it. It stores that charge. Because what do we know about charges, positive and negative ones. Why does an electron stay spinning around the outside of an atom? Because it's attracted to the positive charge of the protons in the nucleus. Yeah? So here, this very thin dielectric here, these two plates are quite close together, so by electrostatics, those two, the positive and negative charges on the plate are attracted to each other, and they don't flow away from the capacitor unless they've got an easy route to do so. Yeah? So it remains charged. If it was a perfect capacitor, it could hold that charge indefinitely. Nothing in this life is perfect, and therefore eventually some of it will leak away. As a case in point, a good quality capacitor will hold charge for a considerable length of time. So you need, they're a piece of kit that you need to be careful with if they've been charged up to like 500 or 600 volts, and then you grab hold of them sometime later, you get a nasty shock, and it isn't very pleasant. Okay, so capacitors connected to mains 400 volt circuits can be charged up to nearly 600 volts, and not connected to anything still hold that charge for a considerable length of time. So just be aware of that. Okay, so they hold a charge Q measured in coulombs C. Here comes a problem. We've got capacitors C holding a charge Q measured in coulombs using the symbol C. I didn't design the system, I just have to teach it. Okay? So the charge stored on a capacitor is Q, is the symbol we use to designate it, and that's measured in a unit called coulombs. We can calculate Q if a current I flows into a capacitor for T seconds, then Q is equal to I times T coulombs. Yeah, so we can find it from how much current flows for X number of seconds. Okay. The problem with that, as you'll find out next week, is if you just leave the circuit to its own devices, current will not stay constant. It will, that will vary. So we'll be covering that next week. Also, if a voltage V is measured across a capacitor C, then the charge stored Q is equal to C times V coulombs. So we can get the charge either from how much current flows for how many seconds, or we can get the charge from the voltage across multiplied by the capacitance in farads. Yeah? And although we use these multiples and submultiples for these formulae, so we use microfarads, nanofarads and picofarads, we must have it in farads. So if you've got a 10 microfarad capacitor, you need to put in that formula 10 times 10 to the minus 6. So we've often got quite small amounts of coulombs in the circuit as well because of that. So the coulombs we're quite often going to be dealing with milli or micro coulombs as well as capacitance. Okay, so that's some different ways in which we can calculate charge values in a circuit. Yeah. So if we're given a voltage across and the value of capacitance, we can calculate the charge. If we're given the charge and a value of capacitance, we can find out what voltage is across a capacitor and so on. Fairly simple 3-variable formula. Like Ohm's law, we can just rearrange it. If we know any two of the values in either of those two formulas, we can use it to find the one we don't know. Okay? It's not proposing to go through too many any examples on calculating those values. Fairly simple. We'll get some within the other questions we have a look at, other examples we have a look at anyway. Okay? What I do want to do is just quickly consider what happens with that capacitor when we discharge it. So there's our charged capacitor. Okay. So I said they're dangerous, and they are if I've got 600 volts or more across them, kind of thing. Quite a lot of stored energy. But when we want to consider discharge, what we do is provide some kind of alternative route, maybe through a switch, and through what's called a discharge resistor. So that capacitor is charged up like a little battery. Yeah? And if we switch that switch on, the positive charges from here are going to flow, a current flow in the opposite direction to what charged it, through that resistor, dissipating some power, so we'll get some heat in there. It's going to, that charge on there is going to do some work. It could keep a lamp on for a period of time. Yeah, you know, you close your car door, your lights go out about 10-15 seconds later. That could be quite a simple circuit like this. Possibly isn't, but could be. Yeah. So we charged it up with a current in that direction. We're going to discharge it with a current in the opposite direction. Yeah. And more about that process and exactly how that works next week, because that's half of the subject of your practical for your assignment, is to use the discharge cycle of a capacitor to determine the value of that capacitor. Alright? So this is discharge. Yeah. So the current flows there now. Yep. You're all happy with that. One last formula, and I think we'll put it on the slide before with the other stuff, is energy stored in a charged capacitor W is equal to half times C times V squared joules. So SI unit of energy. So again, once we know what, if we know the capacitance value and the voltage has been charged up to, we can find out how much energy stored we've got in joules, if that's what we're interested in.
So W is energy.
W is energy, yeah, in this instance. Okay? Yeah. So, moving on. Capacitors in parallel. So we've got three capacitors, C1, C2 and C3, all connected in parallel. No given values at the moment, but let's go back to our 10 volts. When we switch that circuit on and we connect it, a current is going to flow here, some down there, some down there, and some down there. And if the applied voltage is 10 volts, how many volts would we measure after a short period of time across each capacitor?
10 volts.
Yeah, 10 volts. Kirchhoff's law, once that short charging period is what we would term a transient period. Things are changing. Once they're settled down to a steady state, Kirchhoff's law has to apply. So if we take this loop, we've got a 10 volt clockwise arrow. Here, we'd have a 10 volt anti-clockwise arrow there. And there, because that's another separate loop, and we'd have it there as well, because that's another separate loop. Agreed? Yeah? And we get a charge Q1, Q2 and Q3 associated with all those three capacitors. They'd be all the same value, right or wrong?
Depending on what's in each capacitor.
Yeah, depending on the capacitance. So they're not necessarily Q1, Q2 and Q3 in this case, not necessarily all the same value. Yeah, they will be if all the C values are the same, but if they're different then the voltages will be the same on all of them, but not necessarily the charges. So, you might have already looked forward in the notes, I don't know, but how do you think we calculate total capacitance?
Add them all together.
Yeah. So, for capacitors, series, parallel capacitors are like series resistors. We add them together. CT is equal to C1 plus C2 plus C3 plus Cn for any number of capacitors. And total charge QT, Q1 plus Q2 plus Q3 plus Qn. any number of charges. That means they're all connected in one parallel combination. Yeah? We've got the same voltage across them, therefore the total capacitance will be all of them added together, and total charge will be all of them added together. Not necessary that all the charges are the same, because all the capacitance values might not be the same. Yeah. So, one thing further to note, if all C values, capacitor values, in same multiple, e.g. 10 microfarad, 20 microfarad, and 30 microfarad, just add the numbers and answer is in microfarads. Pretty obvious, but if they're different, if you've got a picofarads or a nanofarads mixed in there, then you've got to be careful. You've got to use the powers of 10 notation, or convert your picofarad capacitor into nanofarads into the same multiple. One way or other, you've got to deal with it. Okay? If they're all the same, you can just do the numbers and your answer is in that same multiple. Alright, everybody okay with that so far? And again, I don't think I need to do an example of how we add three capacitors together to get the total. I think we should all be able to do that reasonably well. Right, moving on. Capacitors in series is an altogether different thing. Capacitors in series. If we have three capacitors like that, and we connect it to a source that is 30 volts. Okay, and for the moment I want you to assume that they're all the same value, so I shan't give them numbers because they're all, well, yeah, I will give them numbers, but C1, C2 and C3 same value. Yeah? My question to you is, after the transient period, how much voltage would you expect to be across each capacitor?
10 volts.
Yeah. Well done. It's going to, because they're the same value, it's going to divide up evenly. Yeah? So we would get 10 volts there, 10 volts there, and 10 volts there. Yeah? 30 volts across the whole lot, because that's what's being applied. Yeah? And if we took the battery away, in theory, perfect capacitors, that charge would stay where it is. Because what will have happened is, we'll have got, say, 4 positives on this plate, which will come from the fact that we've had 4 negatives congregate on that plate. This negative charge here will attract some 4 positive charges to that plate, which will have left 3 negatives on that plate, which again will attract 4 positives to that plate, that will leave 4 negatives on that plate. Now, the current that has flown here to give us the overall charge across the capacitor, that current, if we connect a resistor across it after disconnecting the source, can flow back the other way and do some work. Yeah? But this current in here that's flown between those 2 capacitors can't do any work. It just flows back to the other plate. It's energy stored that you can't do anything with. We can't turn it into a heat as those capacitors are connected. Of course, if we separate them, we could put a resistor between them, but that wouldn't really have any kind of effect on the circuit. Capacitors connected in series is really unusual in a circuit under normal conditions. The only real reason you would do it is to try and make up a value you haven't got. Because if you connect 200s in series, you're going to end up with a 50 microfarad capacitor, effectively. But there are issues to doing that. Okay, so series capacitance is quite uncommon, as an uncommon circuit to make, but as a circuit you can end up with because of other factors. Okay, so we're in agreement that we'd have 10 volts across each of those capacitors. Yeah. Everyone happy with that? Yeah? Now, the next bit is, how do you think we calculate the total capacitance of that circuit?
Is it the same as working out resistors in parallel?
It is. Yeah. It is the old C1 to the minus 1, C2 to the minus 1, C3 to the minus 1, plus Cn to the minus 1, all to the minus 1. That will work for any number of capacitors of all different values. Yeah? We can also do CT is equal to C1 times C2 over C1 plus C2 for 2 capacitors. Of any value. And we can do CT is equal to C over N where there are N capacitors of same value. Yeah. So if we got 4,000 microfarad capacitors, we connect them all in series, we end up with a 250 microfarad capacitor. All happy with that so far? Yeah? No questions. What we're going to do now then is have a look at an example for series capacitors. Okay. So if we have 70 volts across that network. Yeah. Let's think about this. What would the total capacitance be? Well, CT is equal to 10 to the minus 1 plus 20 to the minus 1 plus 40 to the minus 1 all to the minus 1 microfarads. Just push the buttons on that for me, please. 1.7? 5.7. Yep. Remember what I did on the previous page with charges. So, despite these being different values, we still get 4 pluses on each of the positive plates. And therefore, still 4 minuses on each of the negative plates. Okay, so what does that tell you about the charge on each capacitor, despite them being different values? The same charge on every capacitor. Yeah? What do you think the relationship between that and the total charge on that circuit? The charge that can do work. Look at the number of pluses and minuses on the outside 2 capacitors. Remember, none of them charges in the middle can do any kind of work at all. All they can do is travel between one plate and another plate. They're charging. All this current can do in here is go that way to charge up and go back that way when it discharges. It's not going through any other component, can't do any work. So we just said each of these have got 4 pluses and 4 minuses. They got the same charge on them, despite being different values. Okay? And the 2 ends have got 4 pluses and 4 minuses on them. The point I'm making here is for series capacitors, the charge on each capacitor equals the total charge. That's fact. That's a statement. That's something you should know. Yeah? So if you can find any one of the individual charges from the value you've been given, you know the total charge and you know the charge across the other 3, 4 or 5 capacitors that are in series together. Yeah? And if you know the total charge, you know the charge across all the capacitors, because that is fact. Yeah? But it's across the combination that is series only. Remember, we're still isolated in series only or parallel only at the moment. We haven't looked at anything to do with combination. Okay, so from what we already know, how do we calculate, and from the formulas I told you earlier, total charge? CT equals, oh hang on, QT equals which capacitance? Be more specific. Total times the applied voltage, V total. I really ought to use E for that, don't I? But I haven't. So we've got 5.7 times 10 to the minus 6 times 70 volts. Push the buttons, please. Got an answer?
times 10 to the minus 6.
Equals 400 times 10 to the minus 6 farads. Yeah, or 400 microfarads. Not coulombs. Coulombs. Yeah. So on each of those capacitors, because the total charge is 400 microcoulombs, so 4 pluses and 4 minuses is equal to 400 microcoulombs. Therefore, we must have 400 micro C there, 400 micro C there, and 400 micro C there. Yeah, everyone following this? Sometimes a little bit difficult to pick this concept up, but we'll get there in the end. Okay, so what we're going to do now is calculate VC1, VC2, and VC3. Okay, have a go at that now, please. Okay, so VC1, how do we calculate that?
Charge over the
QT, because that's the same, over C1. That's 400 10 to the minus 6 over 10 times 10 to the minus 6. And in fact, because they're both the same multiple, you can just ignore that. I believe that come out at 40 volts. Yeah. Following through, QT over C2. (20) times 10 to the minus 6, that equals 20 volts, and this is QT over C3, 400 times 10 to the minus 6 over 40 times 10 to the minus 6 equals 10 volts. What do you notice about those voltages? 40, 20, 10.
halves every time.
Yeah, but that's because I've chosen kind of nice values that do that. That weren't really what I was thinking about. We got 40 here, got 20 there, and we've got 10 volts there.
Yeah, up to V total.
Sorry? They add up to V total. That's a good thing, because we know after that transient period we have to comply with Kirchhoff's law. And in fact, as you'll see next week, Kirchhoff's law is applying all the way through the transient period as well. But that's another point to note. What I was more looking for you to pick out was that the biggest voltage is across the smallest value capacitor. Yeah? So we got 40 volts across the 10 microfarad and only 10 volts across the 40 microfarad. Which I think if I'd asked you to tell me which way round it would be at the start, you might have told me that there'll be 20 across the middle one. You might have had them in the ratio 40, 20, 10. But I think you probably might have said they'd be the other way round. The 40 and the 10 would be the opposite way round. Okay. One of the issues for series capacitance circuits would be a capacitor has another important value associated with it, and that is called its working voltage. So not only will you buy a 100 microfarad capacitor, but you also need to select one that has a suitable working voltage. The working voltage is the maximum voltage you can apply without breaking down that dielectric insulation. Remember, it's very thin. So like anything, if we apply enough force, we'll break it. So if we put 2 ton on top of this desk, chances are that will collapse. But lower weights, it will support. This dielectric will support a certain voltage, but if we apply too much pressure, because that's what voltage is, it's trying all the time to force current through that dielectric. If we push hard enough, it will break. Okay? What tends to happen would be capacitor goes short circuit. So if I short circuit that capacitor, it's like taking it away completely. Yeah? What happens to the voltages in the circuit? We're then going to get 70 volts across those two, the two outside ones. They could quite possibly take them above their working voltage. Yeah? So therefore, we need each capacitor in that circuit would need this one would not need to be at least 10 volts working. It would need to be the full 70 volts working, because it could, under certain conditions, end up with 70 volts across it. Yeah? So that it's very unusual for capacitors to be connected in that way, other than to try and make up an unknown value, or because they exist in regards to other factors within the circuit. Yeah? So we've covered quite a bit of ground already. Store charge, they're a store of energy that can be used. They've got a charge up and discharge cycle we haven't gone into in detail. We'll be doing that next week. We connect them up in parallel. The total is the same as series resistors. We add them together. We connect them up in series. We get the same charge stored on all of them, different voltages across them, and the total is the old C1 to the minus 1 plus C1 to the minus 2 formula, like it is for parallel resistors. Alright, everybody happy with that material so far? Okay. And we're fast approaching 10 o'clock. Alright, what we've got in the second session is the usual thing, plenty of questions to have a go at, and there are some combinations. So when we do combinations here, we do just like we did with the resistors. We break down a parallel part or a series part separately until we end up with either all series or all parallel, and we can get the total, and then we deal with the charges and the voltages in the same way. Okay? Perhaps I might just do one example if need be when we come back. See you either at 10:30 or 11:30 as appropriate.
Hello, man.
At the back. Fine.